Today, we're going to crack a secret code. Seriously. It's a language that's hidden in plain sight, and once you learn it, you can look at a jumble of math symbols and instantly see a shape in your mind. This isn't just another math lesson. It's about unlocking a kind of visual superpower. So, let's get into it.
All right, take a look at this. At first glance, it looks pretty intimidating, right? You've got negative signs, absolute value bars, numbers all over the place. Now, your first instinct might be to just, create a table and start plugging in x values one by one. But that's slow, it's tedious, and honestly, you could completely miss the bigger picture of what the graph is actually doing.
But the good news is, there is a much, much better way, a more elegant way. In this explainer, we're going to break down a really powerful method that lets you build this graph step by step, almost like a sculptor who's revealing a beautiful statue from a plain block of marble.
And every great sculpture has to start with that raw block of material, right? Well, in the world of functions, our raw material is something called the parent function. This is our foundation.
So what is a parent function? It's really just the simplest, most basic version of a whole family of functions. For something like x squared, it's that classic U-shaped parabola. For the square root of x, it's that curve that sweeps off to the side. And for the problem we're looking at today, our parent function is the absolute value of x, which creates this perfect, predictable V-shape. This is our starting point.
Okay, so we've got our block of marble, that V-shape. Now, we need our sculpting tools. And really, every single change you can make to a graph can be sorted into two main toolkits. On one hand, you have adding and subtracting. Think of these as your sliding tools. They just move the entire graph around up, down, left, right. But the basic V-shape itself, it stays exactly the same. Then you have multiplication. These are your shaping tools. They're the ones that stretch, or squash, or even flip the graph over, completely changing how it looks.
Now here's the most important secret to organizing that toolkit. Any change that happens outside the main part of the function affects the graph vertically. That's up and down the y-axis. And these make perfect sense. You add 2, the graph goes up 2. Easy. But any change that happens inside the function, right there next to the x, affects the graph horizontally. And this is where things can feel a little weird, a little backwards.
And here it is. This is the single biggest point of confusion for pretty much everyone. You see x minus 3, and your brain just screams, move it to the left. But in the world of horizontal shifts, it does the exact opposite. So why? It's a fantastic question, and there's actually a really good reason for it. Here's the key. Think about what it takes to get the inside of that function back to 0. 0 is the vertex, the point of our original V-shape. If you have x minus 3, what does x have to be to make that whole thing 0? Well, x has to be positive 3. The input x has to compensate for that minus 3. So the entire graph gets pulled along to where x needs to go, which is to the right.
All right, we have our starting point and we have our tools, but you can't just start carving away randomly. Just like any good construction project, you need a blueprint, a specific order of operations that guarantees you get a perfect result every time.
And here is that blueprint. This is the sequence you're going to follow every single time. First, you deal with everything happening inside the function, starting with those horizontal shifts. Then, you move to the outside of the function, handling the stretches and reflections first, and always saving that final up and down vertical shift for the very end. If you follow this order, you literally can't get lost. And now, for the main event. Let's take our foundation, our tools, and our blueprint, and let's go tackle that original function. We are going to build our masterpiece one step at a time. Okay, here's our target function one last time. Remember, our starting block of marble is the parent, f of x equals x. Just a simple V-shape with its point, its vertex, sitting right there at the origin, at 0, 0. Now let's start sculpting.
Following our blueprint, the very first thing we do is look inside the function for any shifts. And yep, we see that x minus 3. That's our horizontal shift.
And just like we figured out, because x has to work harder to balance that minus 3, the entire V-shape gets pulled 3 units over to the right. So our vertex is no longer at 0, 0, it's now sitting at 3, 0. The shape is exactly the same, but we've moved it.
Okay, we're done with the horizontal stuff. Now we look outside the function for any multiplication. And there it is, that negative 2. This one number is actually doing 2 jobs at once. The 2 is going to cause a vertical stretch, and that negative sign, that's going to cause a reflection. So watch this.
two things are going to happen. First, the 2 grabs the arms of that v and makes the whole graph twice as steep. Then, that little negative sign takes the entire thing and just flips it upside down. It's a really dramatic change to the shape.
We are on the final step. The very last piece in our blueprint is that vertical shift, which is that little +1 hanging on at the end.
And this is the easy part. That +1 just tells us to take our completely transformed graph and slide the whole thing straight up by 1 unit. So that vertex moves from 3, 0 up to its final resting place at 3, 1. And that's it. Our masterpiece is complete.
So, okay, we can make these cool-looking graphs, but why does this actually matter? Outside of a math test? Well, because this whole process isn't just about shapes on a grid. It's a language for describing change in the real world.
Think about it. An engineer uses these transformations to model how a bridge might shift its stress points if you add a new load. An economist models a company's profits, then uses these same shifts and stretches to predict what will happen if there's a new tax or a change in the market. It's the math that describes how systems react to new information.
So let's wrap this all up. What are the key things to remember? First, changes inside the function are horizontal, and they often feel backwards. Changes outside are vertical, and they're intuitive. Adding and subtracting just slides the graph around. Multiplying warps and flips it. And the most important rule of all, always follow the order of operations.
What seemed so complicated at the very beginning is now just a simple set of instructions. You haven't just learned a process, you've learned how to read the language of functions. You have cracked the code.
This skill goes way beyond the classroom. It's about seeing the underlying structure in the world around you and understanding how small changes can lead to really big results. So the final question isn't about math. It's, now that you have this new superpower, what are you going to use it to see?